Shut up and sit down.
Well, hey everybody, welcome back to our 2020 National Electrical Code series where we're teaching you the National Electrical Code of the 2020 edition here on Patreon. And so today's episode, we're moving into part 3 of definitions. Now again, I can't reiterate enough that definitions are critical, and that's why we're taking such time in getting it really detailed, because they are truly critical to understanding how the National Electrical Code works. So without further ado, let's dig into some more definitions. Okay, so what we see here on the screen is we left off previously at exposed, and so now we're at fault current. Now you'll notice that fault current is a new definition in the 2020 National Electrical Code, although we use it all over the NEC. We need to know what fault current is, and it is the actual current that is delivered at any point on the system during a short circuit condition. So wherever your short circuit is, phase-to-phase shorting, okay, not a ground fault condition, okay, so this would be anywhere where there is a short circuit. So the definition of short circuit is phase-to-phase type of faulting. And at that point, you have such high levels of energy, and that is called fault current. So throughout the code, we talk about fault current, we give explanations of fault current, but we really don't define it until the 2020 code. Okay, so as you see here, the actual definition is, what is fault current? It's the current that's delivered at a point on the system during a short circuit condition. So the next one we want to look at is really important because it's also new, not a new term used in the code, but a new term that is defined so we all know what we're dealing with when the question comes up about available fault current, okay? And again, it's listed as fault current available, and parentheses, it's letting you know what it's asking for, which is probably how it's going to be talked about in the code. What's the available fault current? Now, as electricians, we run into a lot of things with transformers at our service equipment, and we need to know what the available fault current is so we can rate our equipment, and we put it on our markings and labels in 110.21 and all these things that we have to mark out. Well, we need to know what that available fault current is. And so it is the largest amount of current capable of being delivered at a point on the system during a short circuit condition, okay? So in our case, a fault current is the value at any point, okay? But then we have the available fault current is actually going to be the value that we work with when something says in the code that I need to know what the available fault current. So where is that on the system? So as you can see in this diagram, you have the source. And the source can be AC or DC, doesn't really matter. So say this is a utility transformer, and they're going to tell you what the actual available fault current is at the secondary of that transformer. Now, you need that because you have a certain distance of wire from that point into and up to the equipment. Now, most times you're going to calculate, you won't know fully, so you'll calculate something based on an infinite bus or whatnot, but usually the utility will give you these values in this scenario, okay, what it is at the secondary. Then all you need to do, there's plenty of apps and formulas that you can use. I recommend the app. Cooper Busman has a great app for this. It's for your phone. It's free download. As long as you know the distance of wire, then you can find out what is the available. So in this example, we have an available fault current right here. That's the maximum available fault current at this point on the node. And then you've got wire, which is inherently going to have some resistance in it, obviously. And then you have a point right here, and this is, say, your service equipment, and this is your overcurrent device, okay? And you need to know what the available fault current is right here, because we need to know the available fault current so that we can make sure that the overcurrent device has an IR or an interruptive rating that is equal to or greater than the available fault current. Now, the equipment itself that the breaker sits in, like the cabinet or the enclosure, also has to have a rating, and that's called a short circuit current rating. Okay, and that is typically going to be equal to or greater than the available fault current. So you have all these things that come into play when you're dealing in this type of circuit, but just important to know that the available fault current is the maximum amount of current during a short circuit condition at a given point in the system. So you'll have available fault current values here at the secondary of a transformer or whatever source it might be, and you have it inherently all the way at the point where the connections make to, for example, in equipment that has an overcurrent device, and you need to know that so I can know what the interruptive rating will be. But important to note that even on the load side, out to a piece of equipment, when you're measuring and your code asks you what the available fault current say for an industrial control panel that's downstream, then you need to know what it is at that equipment so that we know what to rate the equipment, okay? So you don't want it blowing up in people's faces. So you see here that the National Electrical Code has now instituted this infographic, this figure, and it really does help simplify understanding the difference between short circuit current rating, that's the equipment, interruptive rating, that is the device, the available fault current is at any point on the node where I need to connect to another piece of equipment or connecting from a piece of equipment, I can calculate out what that available fault current is, its maximum value. And then we can design the equipment around that, right? Okay. Other things to remember is the term feeder, obviously used a whole lot through the NEC. Biggest difference for people to realize is that a feeder is all circuit conductors between service equipment and the source of a separately derived system or other power supply sources to the final branch circuit overcurrent device. So, easiest way to explain this to people and have a good understanding of feeder is that I have my service here, and from my service I'm feeding a panel downstream. I'm feeding that panel. In that panel downstream, remote distribution panel, some people call a sub-panel, whatever floats your boat. In that, I'm going to have individual circuit breakers or fuses that are going to go out from there out to whatever my load would be, receptacles, lights, a motor, or whatever it would be. And that is the final branch circuit overcurrent protected device. So that's a branch circuit out to the loads. From the panel, service panel to the actual remote distribution panel, that's a feeder. Okay, now, interesting enough, I could have two panels side by side, right beside each other. I'm feeding the one panel with the service disconnect, and now I'm feeding the panel that's next to it. That becomes the remote disconnection means. Okay? Just kind of things to remember. And so in that case, it is downstream, even though it's right next to it, that is a feeder from point A to point B. Now, they do make things like feed-through lugs where both those panels then would be rated as service. It's just a feed-through, and then you have equal ratings of the conductors, the same as it would be for the service, because really you're just extending the bus to another bus, panel board, I guess I should say. Again, just remember for feeders, from the service disconnect to a panel downstream, that's typically an example of a feeder. Now, a feeder can also be from a panel to a wireway where you're going to have taps to that, which would ultimately, those taps are going to connect into overcurrent protected devices like breakers or fuses. It might be from motors, it might be short circuit ground fault protective rated devices. Okay, still an overcurrent protected device, so that would still be a feeder, and it's because you have branch circuits that are connected from the end down to the loads. Okay, so there's different flavors. Just remember for us here as we move forward that a feeder is from a service downstream, okay, to another panel. Again, it's the point between the point between the service disconnect and the last branch circuit overcurrent protected device. Those are feeders, okay? Now, it also talked about separately derived systems. That's important to note that, for example, generators. The supply from a generator, people want to act like it's a service. It's not. Now, some of the rules that you might get into when you're dealing with things like emergency systems might make it act like a service, but again, it's a feeder, okay? From a transformer, secondary side, those are secondary conductors, okay, from a transformer, but they are not service conductors, okay? If I have a transformer outside and it's feeding the building as a service, those are service conductors that come into the panel. Let's just not get them confused. Remember, feeder, from the service equipment or separately derived system to the last overcurrent protective device, branch circuit overcurrent protective device. And then from there, it's branch circuits out to things like receptacles, lights, whatever. I think you get it. All right, let's get back to it. Another couple things that came in the last cycle, again, the field evaluating body. Festoon lights. Festoon lighting, because it's sometimes is low-hanging fruit on an exam. Basically, it's just a string of outdoor lights that are supported between 2 points, like on poles. You see them at festivals, you see them at carnivals, whatever. They literally the lights that are designed to hang to the conductor, and those are called festoon lighting, okay? Field evaluating body, FEB, that's the organization that's going to come out and do a field evaluation on equipment. If an inspector doesn't like the label or it's a piece of equipment that comes out that might be from overseas and it doesn't conform to our normal nationally recognized testing laboratory standards of design, the ANSI UL, then an inspector might say that I need an evaluation, site evaluation or field evaluation, and then you have various field evaluating bodies that will actually come out and do that evaluation, okay? Fittings. Fittings is an accessory such as lock nut, bushing, or other part of the wiring system that intended primarily to perform a mechanical function rather than an electrical function. So a coupling is a mechanical function. Yes, it does serve an electrical if it's a raceway that's being used as an equipment grading conductor, but it's really there mechanically. Lock nuts, for example, are basically a mechanical component, even though in a lot of fittings, it's a very important component to the electrical function of clearing an overcurrent device and things like that. It just remember it says such as, so it's not an all-inclusive when you see this term. It's just giving you some examples. So lock nuts, bushing, and other parts of electrical system, its primary function is mechanical, holding it together, holding the raceway together. But it does, does serve an electrical function. But primarily, it's mechanical in nature. That's what it's there to do. You see, we have some definition, new one of free air. Now, why is this important? Because in the National Electrical Code, and I know I'm blocking some definitions, so I apologize. I will move, let's see if I can't move the definitions to the left a little bit. That way I'm making sure I'm not blocking it as much as possible. And I, again, apologize, but I can only move me on the screen so much. So hopefully I'll move it up here in the middle so you can see it, so it won't be that big a deal. Anyway, okay, so free air. Now, free air is important because when you run cables together, like in cable trays, you're not really separating them, but everybody wanted to use the allowances of free air and ampacity values in 31015 B17, which was in the 2017 code. Now it's just 31017. They wanted to use those free air values for ampacities, which are higher than the normal 31016 that we're dealing with. But if those conductors weren't separated, had a separation, and what was the minimum separation? What constituted that application? It got a lot of arguments. So what if I hung a cable on a messenger and the cable was covered? Maybe it was a tray cable that was being hung on a messenger. Then you had the sheathing, and you could not use the free air ampacity values because you really didn't have the free air aspect of it. So again, this is free air as it applies to conductors, not cable assemblies, to conductors, all right? So now we have a definition. We know when and when we can't apply the free air, especially when we're dealing with ampacities. Of course, we'll deal with that when we get there, okay? All right, so in here it says open or ventilated equipment that allows for heat dissipation and airflow through an installed conductor. So again, tray cable, or if they're installed in a cable tray, or when they're all open in the air, like a service drop or on a messenger or whatnot, they're considered open. And those would be individual conductors dropping down. You have to be careful whether or not they're cabled. Are they really going to allow a dissipation of heat? Okay, but this applies to open or ventilated environments. So we just needed an application that says we need a definition of what free air is, and that's how we've got it. Of course, we have a definition of fuel cell now. We have a definition of fuel cell system. You have a fuel cell in the entire makeup of the system that incorporates a fuel cell in the backup systems, electrical systems that have this backup source power. Then you could have the whole system is the actual fuel cell system, but then you have the individual fuel cell, and you have definitions to that as well. I won't go into those too detailed. Garage. We all know what a garage is. It came to us the last cycle, the clarification. We know what a garage is. It's a building or portion of a building in which one or more self-propelled vehicles can be kept for use, sale, storage, rental, repair, exhibition, or demonstration purposes. All of that is encompassing a garage. So it's more than just that simple garage that's in your house, okay? It could be a garage in a repair building, a rental place. Okay, so understanding garage. So then when we get up to using the applications in say 511, where we're talking about garages, commercial garages, and all those other things, that we kind of know how we're applying things. But we know what a garage is, whether it's our everyday residential garage or it is a repair garage. It's a garage. Now, different rules are going to apply, obviously, per the code, but at least we know we understand what a garage is. We have a new definition here called inverter generating capacity. And what does that mean? When the code talks about this potentially up in, I guess it would be, 690 or other areas like that, it might have a question about an inverter's generating capacity. And of course, it's the sum of parallel connected inverters, maximum continuous output current at 40 degrees C in watts or kilowatts. Okay. Again, we'll talk about probably that when we get up there and how that would apply. But again, this is where you have parallel connected inverters, and you're looking at the maximum continuous output, which is posted on the inverters. Okay. But that's going to give us, when we look at it, what is the generating capacity as it relates to an inverter. It's this thumb. It's the sum of parallel connected inverters and their maximum continuous output, power output, and that is generally posted on the inverter. Ground. Basically, we had a couple cycles ago, we had this long definition of ground. It's really just the earth. So we make connections to ground. We're making connections to earth. In Europe, they call it earthing. Over here, we don't. We just say ground is connection to the earth. We have definitions. Ground fault. Real important. We understand what a ground fault is. We also heard earlier short circuit and a ground fault, all of which are still part of an overload condition. An overload is made up of ground fault, short circuit, or overcurrent, I should say. Overcurrent is a value of three components: ground fault, short circuit, and overload. All of those make up overcurrent. So what is a ground fault? It's an unintentional, means we didn't try to do it, electrically conductive connection between an ungrounded conductor, like a hot, black, red, whatever, blue, hot, of an electrical circuit, and the normally non-current carrying conductors, metal enclosures, metal raceways, metal equipment, or even earth. So a hot conductor makes an inadvertent contact with the metal raceway, a metal box that's bonded, even earth or anything that's connected to earth can create what's called a ground fault. Okay? So ground fault circuit interrupters, for example, is trying to detect this connection quick enough to a connection that is to ground. Okay? And all of these things are non-current carrying parts. There's an important why we have to have a low impedance effective ground fault current path. I guess now we don't say effective, we just say a low impedance ground fault current path. And when we do that, we're going to allow that current to be able to get back to the source, skyrocket at the point of the ground fault, and that's how we have overcurrent devices to trip. That's how we have GFCIs to operate and function, because it can detect leakage on its unattended path. All those type of things create a safe system. Okay, so ground fault is an unintentional connection between any of the ungrounded conductors and the metal enclosure, metal raceways, metallic equipment, all of which, okay, was intended to, under normal conditions, be non-current carrying. Okay, not under a fault condition, it's going to carry current, briefly, hopefully briefly, but under normal conditions, it's not designed to carry current. The next one, we obviously fundamentally need to know what grounded is. When we do something, when we're grounding something or we're making an act of doing something or connecting something to ground, once it's done, it's considered grounded. So when we say a grounded neutral conductor, for example, back at the transformer at the XO, it's a connection that's made to the earth, and at the transformer, then it is the neutral is now grounded. Now, you always, in that case, have a grounded conductor. You don't always have a neutral. It depends on the system. And it has to do with the measurements, and, for example, whether or not you have a grounded system. We'll talk about that when we get to that level. But a grounded is something that is present tense or I guess the result of doing something. Grounding is the act. So it says connected or connecting to ground or to a conductive body that extends the ground connection. A good example of that would be a grounding electrode conductor that goes down to a grounding electrode. That's extending. That's a conductive body that extends that path to that ground connection. Okay. Connection to other electrodes are extending that path. Okay. But the process of doing that is grounding. When it's done, it's considered, after you're done, I guess the past tense is it's grounded. Present tense is grounding, is the active method. Once it's done, it's grounded. Okay? All right, next one is the term solidly grounded. Okay? So that's a connection to ground without inserting any resistor or impedance. So we have some applications where we have a high resistance ground system, and then we have what's called a solidly grounded system. So it's say from a transformer XO to the ground, or I guess from the XO over to the case, and everything connects to earth through your electrode system. Okay, so that is, there's nothing in that path on the supply side bonding jumper. Okay, excuse me, system bonding jumper. Whoa, too many terms. The connection from the XO to case. There's no resistance in there. No resistor or impedance device. So we would consider that solidly grounded. Okay, there's nothing in there. Now, we have occasions where we put high resistance resistors in there or even impedance devices. That means that it's not solidly grounded, but it's replicating the ground reference, and that's what the resistance device is in there for. But it's not really solidly grounded, so that's what this is telling you. To be solidly grounded system, I can't have anything in there that could potentially affect that path to ground. Okay? So that's an example of it. So connected to ground, something's considered solidly grounded. It is connected to ground without inserting any resistor or impedance device. That is considered solidly grounded. The grounded conductor. Very important to understand the terminology. It's a system or circuit conductor that is intentionally grounded. So we talked about a transformer. In a transformer, if I have an XO, which is our grounded conductor, it is connected over with a system bonding jumper and a transformer over to the frame, of which it's also connected from the XO or relative to the XO all the way to the electrodes, which is in the earth. Then that is a grounded conductor. Okay? On a transformer, when we have, for your typical house, you have 12240 volt coming down off the transformer, secondary. Okay? You have that bare, typically the bare neutral coming down, and the reason it's neutral is because you have two legs and the measurements are neutral between each phase A and phase B, if you will, or leg one, or line one, line two to the neutral. It's going to be the same reading. So 240, 120, it's 120 from any leg to neutral, and between the legs it's 240. That is a neutral. Okay, back in the transformer, it is intentionally connected from that conductor to the earth. So it is considered a grounded conductor. You do have ungrounded systems, and that is where you don't have that connection. And there it wouldn't be considered a grounded conductor. It's not grounded. Okay? You could have an ungrounded system. Okay? Not to confuse the term ungrounded conductor, because that kind of has to do with all the hot conductors. Okay? They're all considered ungrounded conductors. But the one that you do take it and you make the connection to, then all of a sudden that becomes the grounded conductor. Okay? All right. Ground fault circuit interrupters, GFCIs. I think we all pretty much have a good understanding what they are. But again, it's a device intended to protect for the protection of personnel that functions to de-energize the circuit or portion thereof, because it could be a breaker, it does the whole circuit, or it could be a device that does the portion downstream of it, okay, where necessary, depending on where 210.8 or other areas of the code tells you to put a GFCI, okay. It says within the established period of time where a ground fault current exceeds the values established for a Class A device. So we refer to this as a 5 milliamp, okay, milliamp nominal. But the code tends to talk about it, as you see in the informational note, based on UL 943. It says, okay, it's designed to, let's look at the informational note, because that's the best way to look at it. It says a Class A, which is what we're talking about, what you're generally going to see in your kitchen countertops, bathrooms, that's a Class A. It says ground fault circuit interrupters trip when the ground fault current is 6 milliamps or higher, and do not trip when the ground fault is less than 4 milliamps, okay? So you hear us all talk about 5 milliamps because it's right there in the middle. So 5 milliamps nominal. So anything over 5, designed to trip. Anything that is less than 4, it's not supposed to do anything, okay? So so we all call it, but to be technical, very technical, it is, again, 6 milliamps and higher, okay, won't trip. 4 milliamps and lower, no, excuse me, 6 milliamps or higher will trip. 4 milliamps or lower will not trip, okay? All right. Again, we just call it 5 milliamps is right there in the middle. That's your threshold, so that's what we refer to. Sorry, don't want to drink that in front of you. All right, next, ground fault current path. Ground fault current path is critical for the operation of overcurrent devices. We size equipment grounding conductors based on ground fault current having a low impedance path. That's why we tie metal parts together. That's why the raceways are done a certain way. That's why we put equipment grounding conductors in. That's why we have equipment bonding jumpers over the devices. This is why we do all this, because we want to establish this low impedance ground fault current path, right? Now, it's an electrically conductive path from the point of a ground fault on a wiring system through normally non-current carrying conductors, like equipment grounding conductors and whatnot, grounded conductors, okay, and equipment, or the earth to the electrical supply source. Remembering, for example, you can never use the earth as a path, okay? It's really not supposed to do that, is that, but it can and will serve a path. And current, you hear the old saying that electricity takes the path of least resistance. All right, well, for years where everybody says that's not true, that's not true. Well, it's not, in a sense that that's how it does. It simply takes the path of least resistance, and all the current that's generated in a ground fault will take that path. It's going to take all available paths, even the some with a high resistive path, and there's some with a low resistive path. We're trying to create the low resistance path, because more of the actual current is going to travel on the low resistive path, because it's less resistance to that current flow than on the higher. But some will take all paths. Okay, it is, again, proportional to the impedance of that path, right? So it says here an example informational note. It says, examples of ground fault current paths are any combination of equipment grounding conductors, metallic raceways, metallic cable sheathing, like a AC cable where the armor is used as an effective ground fault current path, and any other electrical conductor materials such as metal, water, gas piping, steel framing members, stucco mesh, metal conductive reinforcing steel, shields of communication cables, grounded conductors, and the earth itself. All of those things, current will travel on that path. Now, remember, again, when we're talking about establishing things like a low impedance ground fault current path, is slightly different, because a ground fault current path, as you can see, can be many things, okay? But a low impedance ground fault current path that's dictated by Article 250 for the operation of an overcurrent protective device, it is important that we have a low impedance. So we have certain things that in the code under 250.118, but don't worry, we'll get there, that talks about what is considered a low impedance path. Okay, so we've got raceways, RMC, IMC, EMT. We have the equipment grounding conductor, whether it's bare, cover, or insulated, in different types of wiring methods like non-metallic sheath cables and SE cables, and or SER, I should say, it's also in SEU if you're going to use it out to a piece of equipment like an air handler and only need 2 hots in a equipment ground, then you could still use SEU for that. The different things, all of those are designed to create a low impedance path. Don't get confused in the informational note, because some of those things they list aren't necessarily a low impedance. They're still a ground fault. They still could be a ground fault current path because they're conductive, but they're not a low impedance. So again, this is a great example where the informational note's just trying to give you some understanding. Don't lose sight on when we talk about when we need a low impedance ground fault current path. That is where we need to make sure we're using equipment grounds, equipment bonding jumpers. We're using metal raceways that are listed in 250.118. Don't let this imply to you, and of course informational notes aren't enforceable anyway, that the earth is an acceptable path. It's not in our case for the National Electrical Code. It isn't. Just want to make that clear. All right, next. Ground fault protection of equipment, GFP. I see this interchanged a lot in the code. Well, people will say GF, a ground fault protection, and they're really talking about 210.8 for ground fault circuit interrupters. They are different, okay? Very different. This is very different where equipment might require GFP because of maybe it's a thousand volts, or maybe it's some type of system that requires GFP on the equipment. That is totally different than GFCI. The thresholds of where it activates are vastly different. Typically, GFPs can be anywhere from 20 milliamps to 30 milliamps or even higher depending on the equipment and the UL listing for the equipment, okay, and its demands. So don't call GFCIs GFP, okay? And I've seen people call GFCIs GFIs. Not necessarily. That more resembles GFP than it would be a GFCI, okay? So just terminologies, it's better to start off right, given the right terminologies as we're learning these things early on. There's a difference between GFP and GFCI, okay? Now, what is GFP? It's a system intended to provide protection of equipment, not personnel, equipment, from damaging line to ground fault currents by operating to cause a disconnection means to open the ungrounded conductors of a faulted circuit. This protection is provided at current levels less than those required to protect conductors from damage through the operation of a supply circuit overcurrent device. So again, it's less than when we're sizing overcurrent devices, okay? So just keep in mind though, GFP is different than GFCI. Just can't reiterate that enough. And again, it's a lot of times it's real easy for us to just throw things out there and realize that there is a difference. Equipment grounding conductor. For years, people have been trying to get this thing changed to equipment bonding conductor. It ain't happening, okay? It's just, we got informational notes that remind people, hey, just relax. If it's an equipment grounding conductor, let's say in a branch circuit, it's also bonding things together. You have equipment bonding jumpers, and we get it. It's okay, okay? So here you see that it says it is a conductive path or paths that is part of an effective ground fault current path and connects normally non-current carrying metal parts of equipment together and to the system's grounded conductor, that's back at the service, or to the grounding electrode conductor, or both, okay? So, in this application here, typically the EGC is going to run with the branch circuit out, and then if you got a feeder to that panel from the service, then you're going to have, it's on the load side of that service, then that's a feeder, as we talked about earlier. It's going to have a separate grounded neutral conductor in there, and it's going to have a separate equipment grounded conductor in there so that we can float the neutral, basically not making contact with the enclosure downstream, but that equipment grounding bus does make connection to the metal, and that's where you're going to bring all your equipment grounding conductors to it, common location. And that goes back to the source, which is back at the service, which does have a main bonding jumper, and all of that gets connected to the grounding conductor back at that location, back at the service, not downstream. Okay, so equipment grounding conductors are that little bear you see in non-metallic sheath cable. It is, in some cases, for example, AC cable, it's the armor. MC, it's not the armor. It is an equipment grounding conductor that's inside of it, but they do make special MC where the armor can be used as an equipment ground, provided it has a 10 gauge or an 8 gauge, depending on the size, grounding/bonding conductor installed in it. And you just cut that off at the end. You don't terminate that. That's just to make connection to all the convolutions. So you've got all that. And the good news here is we have informational notes. And the first informational note says, hey, it is recognized that the equipment grounding conductor also does bonding. Again, that's to make people feel happy when they're trying to change it to equipment bonding conductor. Okay? Because it ultimately makes connection, okay? Because it ultimately makes connection to the grounding conductor, which makes connection to earth, it's more justified to be called equipment grounding conductor, okay? Because it's also stabilizing the voltage all the way through the system. So it makes more sense to keep an equipment grounding conductor. And it does serve a bonding function. So again, just to clear. And here, we also gives you a list at 250.118 to let you know what is considered an acceptable equipment grounding conductor. And it's a long list, okay? Grounding electrodes, what are those? Okay, it's a conductive object. It used to say device, but that was the wrong terminology to use. It is a conductive object through which a direct connection to earth is established. Ground rods, it's directly driven into the earth. Okay, that is a grounding electrode. Okay, it's an object that we connect to with the grounding electrode conductor in order to make that connection, that intimate connection with earth. Same with a concrete encased electrode. That's a grounding electrode. A water pipe ground that's in the earth, it's metal, it's 10 foot in contact with the earth, where you have one, very rare today, that is a grounding electrode. So we have a list of grounding electrodes that are in 250.52, and that tells you all of them. And so those are making a direct, intimate contact connection to earth, like a ground ring makes connection into the earth, okay? And of course, we'll cover all those electrodes when we get there. Now, the connection from that electrode to the grounded conductor in the service, for example, or to the XO point in a separately derived system, that is called a grounding electrode conductor. And we call that a GEC. That's our acronym we like to use. So it is a conductor that connects the system grounded neutral or the equipment to the grounding electrode or to a point on the grounding electrode system, okay? So again, a point on the system. So transformers, for example, that be from that equipment, making a connection to the electrode, that's going to be a grounding electrode conductor, okay? From the grounding conductor in your service to the electrode, that's a grounding electrode conductor, okay? So those are examples where that connection is being made. Another thing to discuss is sometimes in the code, it might reference something that's guarded, okay? Whether or not you're on top of a roof and you have conductors and it says it has to be guarded. Or you have something that says certain equipment has to be guarded. What does the guarded mean? And it means that it is covered, it is either shielded, it's fenced, it's enclosed, or otherwise protected by means of suitable cover, a casing, a barrier, rails, screens, mats, or platforms to remove the likelihood of approach or contact by persons or objects to the point of danger. Okay? Now, again, you can't save people from total stupidity. All you can do is try to mitigate the potential of stupidity. Okay? That's the best way to say it. So when we guard something or something's considered it's guarded, means that you have put something around it, some kind of a casing or barrier or something, maybe you even enclosed it in order to keep people from coming in contact with it. You're saving them from themselves, okay? That's what the term guarded is when you read it in the NEC, okay? And a guest room or guest suite, when you're dealing with a hotel or motel, really pretty clear-cut definition. It accommodates living, sleeping, sanitation, and storage. You notice it doesn't say anything about cooking at all in this application. It just says storage, sanitary, sleeping, and living. If it has cooking involved in it, then it's probably a dwelling unit. Okay. And then a guest suite is an accommodations with 2 or more contiguous rooms, comprising of a compartment with or without doors between such rooms that provide living, sleeping, sanitary, and storage. So a suite might have, I've been in rooms where you have one room and just one sleeping area, right? And then there's some that have like a 2-bedroom, and you call it a suite. So the rooms, 2 or more rooms are comprising, and again, you don't have to have the doors to separate them, but between these 2 rooms, and you have living, sleeping, sanitary, and storage room, whereas a guest room is just simply everything's involved in one room, but then you could have a guest suite. Both of these still fall under the normal applications when we're talking about the National Electrical Code and we're dealing with things like spacing in 210.62, I think. I can't remember, but talks about receptacles and things like that. So, I mean, you've got some rules. Don't quote me on that code reference. But there's applications where it's important to know whether or not you're dealing with a guest room and guest suite versus something that might be a dwelling unit. Okay? Habitable room. Brand new for 2020. It's important we know what a habitable room is because we have so many things in the code that make reference to non-habitable rooms. Okay, attic spaces that are not to be used as habitable spaces. For example, when we're doing load calculations, what does that mean? So I need to know what a habitable room is so that I understand what a non-habitable room is, right? So it says it's a room in a building or for living, sleeping, eating, or cooking, but excludes bathrooms, toilet rooms, and a toilet room would be a bathroom that doesn't qualify as a bathroom because it didn't have a sink in it. Okay, it might just have that little space that has a toilet in it, and that's a toilet room. Okay, closets, hallways, storage, or utility spaces, and similar areas. Okay, good example is it says closets, but you notice it doesn't say closed closet because a closed closet is very similar, obviously, to a closet in this case, and I would not treat that as a habitable room. That would be an uninhabitable room, okay, or a non-habitable room, however the code likes to say it, okay? A lot of definitions, again, as I always say, I'm not going to cover every one of them because they're pretty self-explanatory in your studies. The next one we're going to look at is with the term identified. And something is said into the code to be identified, okay, like an identified handle tie on a 2-pole breaker or 2 single-pole breakers. For when you're doing a multi-wire branch circuit, you notice it makes the reference to identified. It is recognized as suitable for a specific purpose, function, use, environment, application, and so forth, which describes in a particular code requirement. So when it says something is identified for the use, then that means it is physically identified for its application. So an identified handle tie is identified to go on 2 single-pole breakers to make them act as one, okay? So if I have something that's identified for a condition of use, okay, then it means it's been evaluated for that environment, that purpose, or even that specific application, okay, then it is identified, okay? Here's one that people should know, make sure you know just in the general course of understanding, is in sight from, which in the code might be referred to as within sight from. Within sight, just remember that there's 2 components to this. One, it literally has to be within sight. You got to see it. And 2, it cannot be more than 50 feet from you. So if it was 55 feet, it is theoretically still within sight, unless you can't see like me, but it's still within sight, but it doesn't qualify when it comes to the NEC as being considered in sight from, or within sight from, or within sight, okay? That's kind of like you go into a football game and your son is kicking a field goal from 51 feet, and you're a code nerd, right? And you're watching this, and your son kicks it and they make it and they win the game. And then the son comes home and says, Dad, did you see me kick that 51-foot field goal? And in my mind, I look at him and go, no, it wasn't within sight. It wasn't within 50 feet. It's 51 feet. But I won the game, Dad. For me, code, I didn't see it. Sorry, I didn't see it. It's not reality, but you get me. You get what I'm saying. From a code person's perspective, it's got to be within 50 feet. It can't be around a corner and still be only 25 feet away and say, hey, it's within 50 feet. Nope. If I can't see it, and it's not within 50 feet in my mind. It is physically within 50 feet, but it is not when it comes to the NEC. Okay? Two components there you have to keep up with. Information technology room. The reason we talk about this one is because you'll have a 645 that talks about IT rooms and things like that. So what is an information technology equipment room? It is a room within an information technology, it's a room within the information technology equipment area that contains the information technology equipment. And of course, we have information technology equipment right here, and that talks about the specific equipment, okay, that we're dealing with. All right, so, but the equipment room is inside of the information technology area, and it's a space just for that IT equipment, okay? And instantly, it's a good time to explain this right here. When you see this anywhere in the code, bolds, and then you see these references, this is your code sections in NFPA 75. And that means that this definition came from another document, okay? It was extracted and placed in here, okay? So it's been copied verbatim, all right? So that's when you see that right there, that lets you know where this definition actually came from. So Code Making Panel 5, which has the purview over this definition, actually pulled this definition from NFPA 75 document, and then they gave it to Article 100, which is Code Panel 1, in order to put it in Chapter 1. Okay, so that's how that works. And this out here, again, just reminds you who has the responsibility for the definition inside of this Chapter 1. Okay, so Chapter 1 is the body that oversees the whole definition scope, but each other article are in charge of certain definitions for them. And that's where you see the CMP 12. Okay. See this one here for interactive inverter? Yes, it's in Article 100, but Code Making Panel 13 is the one that retains control over the definition. Okay. All right. So that's that. Now let's get down to this one here. Interruptive rating. 110.9 and 110.10 talk about short circuit current ratings and interrupting ratings, okay? Where the short circuit current ratings is equipment, the IR ratings is the value of the device, okay? And what is interrupted rating? It is the highest current at rated voltage that a device is identified to interrupt under standard test conditions. So it's been tested. So if you have a circuit breaker and it's a 10,000 IR interruptive rating, then it's been evaluated to handle current at that voltage. What if it's a 120 volt circuit breaker? It can handle current up to 10,000 amps, okay? All the way up to that current, up to that voltage's test rating. So that's why it got the 10,000 amps. So that's why it's so important for us to know what that available fault current is, okay? So main breakers, for example, if it's residential, it might have a 22,000 rating on it, interruptive rating. So again, we need to know what the available fault current is to that equipment so that we know that that breaker is not going to blow up in somebody's face when there's a short circuit somewhere. It causes that breaker to be tested, okay? So that's why we have all this available fault currents and all these things that we're trying to test for, okay? An informational note says, for example, equipment intended to interrupt current at other than fault levels may have an interruptive rating implied in other ratings, such as horsepower or even locked rotor current. Okay, so you have other ratings that you could have the interrupting current other than fault levels. Okay, So you could have something that's rated in horsepower. You could have something rated in locked rotor current. Most of the circuit breakers that we see, main breakers and panels, things like that, have an IR rating, and it's actually the current rating at the applied voltage, and that is the highest current that it can experience, that can handle and work safely. So that's why we need to know what available current is, and that's how we have to know that. Intersystem bonding termination. So this is that little connection that is made at your meter or service equipment and at detached structures that have communication systems and things like that, Dish Network, DirecTV, all those type of cable lines that come in. So we have what's called intersystem bonding, and that's connecting all of the connections for communication systems together and then connecting them to the grounding electrode system, generally for lightning dissipation and things like that. So that's called an intersystem bonding termination, that point on the system where you take all of those bonding conductors for all of these communication systems and you bring them together and then you connect them directly to the grounding electrode system. Okay, that's what an intersystem bonding. Now you see there's a bunch of new definitions for things like inverter, inverter input current, inverter output circuit, multi-mode, and island mode. All of these existed previously. They're new here, but they were found up in the applications in like 690 and things like that. Okay, so they were already there. They're not new in like, oh, we just created them. Okay, and so an inverter, what's an inverter? Equipment that changes DC to AC. Okay, a converter changes AC to DC, but an inverter inverts it and it changes DC to AC. So if you ever wondered the difference between an inverter and a converter, okay, just remember converter plugs into the wall, right? So it's got to take AC and make it DC. An inverter is the opposite. It's taking DC, turning it to AC. So inverter, converter, just so you know the difference. What is inverter input circuit? It's the conductors connected to the DC input of an inverter. So if I have an inverter that's for like a PV system, it's the conductors connected to the DC input of the inverter, okay? So you're coming in from the DC source in to the inverter, it's still DC, and it's going to go into the inverter because ultimately it's coming out of the inverter as AC current so that we can use it, right? Then you've got what's converter output circuit. And again, that's conductors connecting to the AC output of the inverter. So I've got a photovoltaic system and the DC is coming from the strings and arrays coming down through disconnect into the inverter. And that is going to be through the inverter input circuit. And then on the output circuit, it's converting it, if you will, or inverting it, I should say, over to AC, right? And then it's coming out. So that's the AC output. Important to understand these references because when you get up there, there's applications of percentages and things that have to be applied to some of these values, and you need to know what an inverter output circuit is. You need to know what an inverter input circuit is. So when we get up there into 690, these things, for example, will make more sense, okay? And it's obviously not just in 690 because it's in 100, so that means it has to be in more than one article. So there's other aspects where it will be. Next, you have multi-mode, and that is basically equipment having capabilities to act as both an interactive inverter, that means interact with the utility, and it can stand alone on its own. It does not need to interact with the utility. In other words, you lose utility grid and it switch over. So if it's multi-mode, it has the ability to work as a standalone, or it can work as an interactive inverter. Most of the ones that connect to the utility system are interactive inverters, but a lot of inverters, if they have a multi-mode feature, can operate and act as a standalone. It doesn't necessarily have to be connected to the utility to function, okay? Next, we have what's called an island mode, and it is a specific operational mode. It says the operational mode for standalone power production equipment or an isolated microgrid. So we have a definition of microgrid when we get there. We'll talk about it. Or for multi-mode inverters or an interconnected microgrid that is disconnected from the electrical power production and distribution network or other primary power source. So it's connected away from it, or it can be isolated away. And so we used to refer to it as an isolation And now we just call it islanding. Means it isolates it out by itself, disconnects it, still functions, but it's functioning in what we call an island mode. It's just a specific mode that allows it to stand alone and operate it without the assistance of things like microgrids, which is a connection of other supply sources, whether it's a combination of PV, wind generation, flywheel, whatever it might be, that are both feeding what we call a micro DC microgrid. Don't worry, when we get to microgrids, we'll talk about it a little more. Point is, you have multiple sources coming in. All right. This is a mode where the inverter can operate and say, timeout, timeout. I'm operating by myself. It's kind of like that island that's sitting in the middle of your kitchen. It's not connected to anything. It's not a peninsula. It's an island by itself, and it's saying, I want to be treated as an island. Nope, stay away from me. Okay, that's what we're talking about. All right? It's best I can explain it. All right, next one that's important, obviously, for us. We know what a kitchen is, but it is real important that we understand that a kitchen is an area with a sink and permanent provisions for food preparation and cooking, okay? So it has all these elements to be a sink. Note it doesn't say an area with a sink or permanent provisions for, it has ands in there. And the ands are chained, means it's this and that, not this or that. So to be a kitchen, it has to have the sink, it has to have permanent provisions for food preparation and cooking to qualify as a kitchen. Now you're gonna have areas that are not kitchens. But the code now has said, look, we're going to give you other provisions for GFCI requirements. For example, if it acts like a kitchen, but it doesn't have the cooking in it or something like that, okay. But we're going to give you some rules for protection like GFCI and other things. We're going to say that it's acting close enough like a kitchen. But it's important that you know what a kitchen is because we have rules for kitchens that we have to be aware of in 210.52, okay, for receptacle spacing and placements and things like that, okay? All right. Labeled, again, it's equipment or material in which has been attached a label, some kind of symbol or other identifying mark of an organization that is acceptable to the AHJ, like a nationally recognized testing laboratory, UL, ETL, which is Intertech, Met Labs, or whatever. They will apply their label, their mark, okay, and it tells us that it's been inspected, evaluated, or whatnot, and it's good to use. Okay, it meets the appropriate standard for whatever's being used. Example, MC cable, UL 1569. That's an ANSI UL standard. When we apply the labels to the packaging, because you don't have to apply it to the cable itself. It's metal, for goodness sakes. But if you apply it to the labels on the packaging, then we are basically labeling, telling you that it has been evaluated. It was constructed, manufactured, and a third party, non-interested party, okay, has come in and evaluated that, yes, so-and-so made that product to the minimum standard that's required, okay? And that's what labeling is, and that's physically a label, okay? Laundry area. We have a definition for laundry area. It says an area containing or designed to contain a laundry tray, clothes washer, or clothes dryer. Okay. Interesting enough, a clothes dryer is not required equipment. Okay. A washing machine or laundry circuit is required, but a clothes dryer circuit or separate, 240 volt application to a clothes dryer is not a requirement in the code. However, we do have rules in 220.54 for dryers if we're going to put one in there, and most places do, but you still have the requirement, in the laundry circuit. Now, there's some exceptions to that rule if you're like apartments, complexes, and they have a laundry facility on site, but don't worry, we're going to cover that as well. Just understand what a laundry area is, okay? It is the area that's where you would have a laundry tray, clothes washer, or a clothes dryer, okay? Or even that area that might have none of that stuff, but it is designated to have that stuff. So example, if I were to put the water supply there with the drain for a washing machine, yet nobody had a washing machine there, somebody can't argue, well, it's not a laundry area, the clothes washer's not there. No, it was designed for it. Whether it's in there or not is irrelevant. It was designed for it, so it's a laundry area. Why is that important? Because now we have GFCI requirements, AFCI requirements, and all this for laundry areas, okay? Even the dryers in a laundry area now, in a dwelling, for example, is going to require GFCI protection, okay? Big changes in 2020. Okay, next, lighting outlets. There's many types of outlets. You have receptacle outlets. We have lighting outlets. So when we go through the code, you'll see reference to outlets. Okay, just remember that's not a receptacle in itself. An outlet is a point on the system where we make a connection. Okay, and different types of utilization equipment make a connection to it. So in this example, what is a lighting outlet? It's an outlet intended for the direct connection of a lamp holder or luminaire. So lighting outlet, whether it's on the wall or on the ceiling, has the wires in the outlet box. That's why they call it an outlet box. Okay, and you're going to put a luminaire on it. And a lamp holder, incidentally, is like a keyless, which is just a keyless with a lamp, which people refer to as a light bulb, but it's a lamp. There's very limited applications where you can use that. Obviously not in closed closets, have to be totally enclosed. But at any rate, a luminaire is a full assembly. Okay, and we'll see that definition here shortly. But a lamp holder is the lamp is holding the lamp, but the lamp is the bulb itself, I guess you should say. And you're making that direct connection to it inside that outlet box. Okay, so when we see something like outlet in the code, don't think receptacle, because we're so used to saying, hey, look, you got an outlet right there. Yes, it's a device that is in an outlet box, and you could refer to that box as a receptacle outlet. Okay, but the actual device that goes in it is a receptacle, okay? You get my point. Track lighting, okay? It's a specific track. It says a manufacturer's assembly designed to support and energize luminaires that are capable of being readily repositioned, turned, moved, slid on the track. Its length can be altered by the addition or subtraction of sections of the track. So I can add to it, take it away, whatnot. We need to know what lighting track is or track lighting is, because when we're doing calculations in Chapter 2, which is in Article 220, we need to know for track lighting, because we have some values in VA that we have to establish to track lighting. So we need to understand track lighting a little bit. So again, definitions here. When a product is listed, okay, then it means that that equipment or material or services, including in a listed, published by an organization that is acceptable to the AHJ, like an NRTL, Nationally Recognized Testing Laboratory. Okay, that means that it's been listed, it's been evaluated. Okay, it meets a certain listing, and once it meets that listing, it's considered listed. And in most cases, probably all cases at that point, we're going to do different things like labeling it. So here you see an informational note that kind of gives you a good understanding. It says, the means for identifying listed equipment may vary from each organization concerned with equipment evaluation, some of which do not recognize equipment as listed unless it is also labeled. So many organizations, AHJs, different things, will say, look, I'm not going to recognize this as being listed unless I see a label on it, okay? Again, some may vary. It says, use of a system employed by a listing organization allows the authority has jurisdiction to identify a listed product. Okay, so again, having listing, a lot of times you can go to the website, you can go on the internet and see whether a product's actually listed. Manufacturers basically will list their product, they will label their products for the most part, or put some kind of mark on there that it establishes that it is a listed product and that it was evaluated by some organization, okay? Like UL or ETL or MetLabs or CSA or FM, or there's a bunch of them, right? Okay. Now, let's come to, we have live parts. So we see this a lot in the code. Basically, it's energized conductive parts. All the guts, it's not just wire. It's all conductive live parts. The bus bar, if it is live parts when it's energized, okay? All this type of stuff are energized while it's live, right? So it's a live part, okay? Damp location, dry location, wet location. 3 different physical types of location. So let's understand these and I'll give you some examples. So what is a damp location? It is locations protected from weather, but not subject to protected from weather, but not subject to saturation with water or other liquids, but subject to moderate degrees of moisture. Great example of this, and it gives you some examples, is under canopies, open roof porches, which is, again, it's not really subject to saturation, but it could be subject to condensation. You could have moisture in the air. Okay, but it's protected directly from the elements. So it is subject to moderate degrees, but it would be easy to say that any open porch or locations like that are subject. But it also could be interior locations that are subject, like basements, crawl spaces, things like that, could be argued that it's a damp location. And then some people could argue, depending on how sealed up the crawl space is, that it's a dry location. Okay? Again, all in the argument. Just don't fall for this, such as it says some basements, some barns, some cold storage. Just because it doesn't say crawl space doesn't mean that if I get into crawl space and I see moisture down there, okay, puddles, pooling, I would argue that that's a damp location. If I get down there and I see it's dry as a bone and it's sealed in well, then I would argue it's a dry location. Again, AHJ's got to make that call, but again, we're trying to make this determination. Now, a dry location. What's a dry location? Any wall construction where the wire is going to be in the actual wall framing members and things like that, then that's a dry location. Okay? It says, so let's look at it. It says a location not normally subject to dampness or wetness. It says a location classified as a dry may be temporarily subject to dampness and wetness, such as in the case of a building under construction. So what does this mean? Okay, so I'm framing up a building. It's a wood frame, make it easy. And I'm pulling non-metallic sheath cable in it, which incidentally is a product that's rated for dry location. So is MC, by the way, if you don't put a PVC jack covering on it. So we're just talking dry location. And all of a sudden a storm comes in. Now, if moisture or some wetness or dampness gets on the cable assembly, that didn't remove the fact that it's still a dry location. Because remember, the wood framing members all got wet as well. They're not going to rip those out. The caveat here, and we refer to from a manufacturer's standpoint, is to look at the NEMA Evaluating Water Damage Guide. And it'll immediately say things like non-metallic sheath cable have to be ripped out. I'm going to say that that is not 100% accurate on the fear of getting in trouble with all these manufacturers who would love us to rip it out. I say that it's on a case-by-case basis. Because if you only had moisture go across the sheathing, okay, then if it only goes across the sheathing, then it's no harm, no foul. That PVC material is going to protect it, okay? Now, the difference is if it got into the boxes so that it got into the end of the cable assembly so it can get into the paper, then that's a problem, okay? And so then it would warrant removal. But the reason we have this statement here is it says that it's a dry location, but it can be subject to temporary conditions of dampness and wetness, and even gives you an example of a building under construction. And again, it says that's just an example. That's not all potential cases. So, again, the caveat to this is contact your manufacturer if you run into this condition and let them give you guidance on it. But just because wire, let's say it was in a ceiling of a 2-story building and a sprinkler system went off and the water came down and you have horizontal non-metallic sheath cable and some water came over top of it. Am I really going to rip all that out just because it got exposed to some water? Absolutely not. Now, the ends didn't get caught up in it. Now, if it got into the luminaires, that's a different thing. We're talking about across the cable. I don't think it's necessary to pull it all out. I think it would be a bunch of hype. Now, some manufacturers would want you to do that. I'm going to tell you that even though I represent a manufacturer, I'm never going to tell you to do that. But it's all based on the conditions. Once you tell me the condition, then I have to make a decision. Okay? If it was saturated and flooded and it sat underwater long term, then I'm going to tell you to take it out because I don't know what was in that water. If it was gravitationally applied, like with sprinkler system, it just hits some of it and then it runs off of it, it's not suspended or submerged, then I'm going to say no harm, no foul. So again, the conditions of use will vary. Okay. Next, a wet location. What is it? Installed underground. So all underground installations are wet locations. Remember that. Doesn't matter if the raceway is a sealed up PVC and you think that it's going to stay dry in there. It's not. Okay. So also, any concrete slab or masonry that is in direct contact with the earth, slab on grade, any of that raceway, any of that conduit, any of that that's installed, okay, is considered a wet location. Okay, keep that in mind. It says, in locations subject to saturation with water or other liquids, okay, it's not just water, such as vehicle wash areas and unprotected locations exposed to the weather. Okay, so outside, if it's exposed to the weather, that's the different thing. So the difference between a wet and a dry is that in the wet, it's expected to be always exposed to this potential for this condition. The dry application, which allows for a temporary dampness or wetness, is wetness, not submersion, not total saturation. It's just wetness. Another example, I took a piece of wire and I sprayed some water on it. It's just wetness. It's going to end up drying, and it's going to end up in a location ultimately, when it's all done, that's a dry location. So the people that freak out about some slight rain or some water that gets on NMB in a building, I think maybe you should worry more about the wood studs that are getting wet, or the insulation that might be getting wet, or the subflooring that might get wet. But nobody seems to worry about that because it'll dry out, right? Because ultimately it's a dry location at the end of the day. Let that be your guide, okay? All right, the next thing we'll end up on this session is luminaires. Many people refer to light fixtures as, they'll say light fixture, and that's okay. We all know what it used to be light fixture. And then it changed to luminaire, which is a more broader term. Now, luminaires are not lamp holders, as I talked to you earlier. That's just a lamp, like a light bulb, but it's called a lamp, screwed into a base. That's just a lamp holder, okay? That's not a luminaire. But a luminaire has a lamp. It has the parts designed to position that light source, okay? And it has the ability to connect it to the power source. For example, a fluorescent. You have the light source, you have the ballast, you have the diffuser. In many cases, you have the lamp. All of that makes up a luminaire, okay? Just a light bulb or a lamp, it's the accurate name for it, even though Thomas Edison will be rolling in his grave. It is a lamp. It is actually, when you just do that, it's plugged into a lamp holder. Now, that's not to confuse a luminaire that might have an exposed lamp, okay? A lamp holder is very specific. I'm sure you all have seen it. We refer to them many times as keyless. And it's just basically a porcelain or plastic base that the lamp screws into. Some of them have a pull chain on it, some do not. And it goes on a lighting outlet, okay? That is called a lamp holder. That is not a luminaire, okay? So what is a luminaire? It's a complete lighting unit consisting of a light source, such as a lamp, together with the parts designed to position the light source and connect it to the power source. It also may include parts to protect the light source or the balance. That would be the shield, for example, or to distribute the might be a diffuser. All of that is part of the luminaire, okay? All right. Well, that's a lot in this episode as we're moving through these definitions. Hopefully you got something out of that and you understand these definitions just a little bit better as we kind of just talking through them. You get a little better understanding of what they are and for use as we move through the National Electrical Code. So stay tuned for the next part, and we'll just keep knocking out these definitions.
Shut up and sit down.